This was the question which was asked in NEET 2025. The question says that in an oscillating spring mass system, a spring is connected to a box filled with sand. As the box oscillates, sand leaks slowly out of the box vertically. Now this word vertically is very important because this has been interpreted in a very wrong way. So continuing with the question, we have to find the frequency omega t and the amplitude at of this system. So starting with, I will first point out that what most of the solutions that I have seen on internet, they have given this answer 3 as correct, in which omega is increasing with time and amplitude is decreasing with time. But this is not correct answer, and I will explain you why. So this is our spring mass system. Suppose this is the spring fixed at this fixed end, and I have deliberately chosen this diagram. I will explain you why this diagram is correct as compared to a vertical spring mass system which has been shown by various solutions in which they have used this kind of arrangement where the spring and mass is vertically arranged and sand is leaking. This is not possible, and I will explain it why with some leakage. So let us first consider the equation of motion. We start with Newton's second law. So the equation is kx plus this ma, which we generally use kx plus ma equals to 0. But in this case, it is not ma, it is rate of change of linear momentum. That is d by dt of mv, and this equals to 0. Now for this case of simplicity, I have assumed that mass, obviously it is mentioned that some sand is coming out of this box. So I have assumed it a linear function of time. So I have chosen mt equals to m0 minus at. Now if we differentiate this rate of change of linear momentum d by dt of mv, then we will see that if we differentiate it d by dt and we substitute the value of m as m0 minus at and multiplied by this velocity is replaced by x dot. So after differentiation we will get minus ax dot and plus this m0 at into x double dot. It is a simple differentiation, you can cross check it. And then substituting the value of this d by dt, suppose I am writing this as equation 1. So substituting this value and this I am writing it as 2. So substituting the value of 2 in 1, we finally get kx minus ax dot minus m0 at x double dot equals to 0. So after rearranging, the equation is something like this. This is our final m0 at into x double dot minus ax dot plus kx equals to 0. And in the differential form it is m0 at d2x by dt square minus a dx by dt plus kx equals to 0. Now this is a very familiar form of equation which we use when we have a damper. For example, this is our spring mass system having mass m and spring constant k, and this is the damper having damping coefficient c. So the standard equation is like this. This is our standard equation, mx double dot plus cx dot plus kx equals to 0, which a very known equation. And when we solve this, you can pause this video and see the solution. We get various cases where that is underdamped case or critically damped or overdamped depending upon the value of c. So in all the three cases, what is important is that you can see that the amplitude is gradually decreasing. This is the case of overdamped. In this green line is critically damped and this red is our overdamped. So in all the three cases, amplitude is decreasing. Why this amplitude is decreasing is, you can see from here that this damper is kind of it is absorbing energy, so energy is gradually decreasing. So we can say that this C is absorbing, which is our damping coefficient, is absorbing the energy. But in our case, if we talk about our equation here, we have this value minus a, where a we have assumed it to be positive constant. So this is minus a, means we are having a negative damper. So what this negative damper is doing is, it is in fact providing energy to the system. So now the question arises, how this this negative damper, sorry for writing this, just to remind you that this minus a is acting as a negative damper. So this will provide energy to the system. So if we solve the equation, this is our standard equation where we have used this mx double dot plus cx dot. So plus this positive damper is absorbing the energy, and the negative damper will provide the energy. So if we solve this equation, this is our equation where we have this minus c and modulus of c. So this is our negative damper, and if we solve this, you can again pause this video and see the solution. The solution that is available for x with time is something like this. So here you can see the amplitude is increasing with time, and also the frequency is also increasing. In order to be doubly sure, I have plotted this differential equation which we have obtained, that is m naught minus 80 into x double dot minus ax dot plus kx equals to 0. So in this you can see that we have the amplitude which is increasing, and in the same way, if we talk about this interval 0 to 5, you can see we have two peaks, and when we have the interval 10 to 15, we have three peaks. So it means the frequency is also increasing. So the overall amplitude is also increasing and frequency is also increasing. So the correct answer of our question is this one, where we have both amplitude. This is the correct form of correct answer, where both amplitude as well as frequency is increasing. Now as far as the examination is concerned, because in order to solve that differential equation it requires Bessel's function and all that, I will post that derivation in the link. But as far as, because there are very paucity of time, in 60 minutes student have to solve 45 questions. So how they will approach this question is, I will again repeat, what you have to do is, you have to first write the equation. This is what is required. You have to start with equation number 1, that is the kx plus rate of change of linear momentum equals to 0. Then you can assume whatever means linear or non-linear also, t square or something, but for the sake of calculation you can take the value of mt as m naught minus 80, and then you get this differential form of equation. Once this differential form of equation is available, by intuition you can say, first part is here you have to find omega. So this you can directly substitute, that is root under k by m, and m is changing with time, and in fact it is decreasing with time. So we can say that angular frequency will increase. So angular frequency will increase. This can be interpreted from here. And for the amplitude part, which I don't think there is sufficient explanation why they have given negative or some random explanation are there. The simple differential equation says everything, because we have a negative damper which is like energy provider or energy supplier, and since this energy is supplied to the system, its amplitude will increase. This I have confirmed with this is for positive damping and this is for negative damping, and this is the case that I have plotted in MATLAB to confirm that of course this solution is correct. Now coming to the question, why I have not chosen this vertical spring mass system. Let us start any system having mass m and velocity v. Mass is varying with time. So when we consider both the system, means the losing mass as well as the mass that we are having, so in that case we have this linear momentum as conserved. So when we write d by dt of mv equals to 0 and we differentiate it, what we get is mv dot plus m dot v equals to 0, and after rearranging we get this equation. Now since the system is losing mass, so m dot will be negative. So this negative and negative will become overall positive. So v dot equals to m dot by m into v. So this quantity is greater than 0. So we can say that we are getting acceleration. So far so good. But this equation is not fully correct. Let me remind you, this equation, when we are using differentiation, this assumes either we are picking the mass which is at rest, or when we are ejecting the mass momentarily comes to rest. Only in that case this equation is valid. So please remember that this equation is not entirely correct and you cannot blindly use it. So this equation is only valid for this special case for our question, when the mass, for example the sand which was falling from the box, if it comes momentarily to rest, only in that case this equation is valid. So there is no chance, means I cannot say that it can provide as it is happening here, that the acceleration is increasing, which is a false hypothesis, and in fact it is not correct. Now I will explain why. Let us take this simple spring mass system which is in vertical direction, and suppose the sands are coming out with the same velocity with which this uh, block is moving. This del m is having the same velocity v. So initial linear momentum before ejection is m into v. M is the total mass and v is the velocity with which this spring was mass was vibrating at the instant when we are talking. So when the mass is ejected, the remaining mass is m minus del v, m minus del m, and the velocity is suppose v dash. And we have assumed that the ejected mass is having the same velocity v. So this is del m, our ejected mass, and this is our velocity v. So final linear momentum is m minus del m into v dash plus del m into v. When we apply the conservation of linear momentum, that is the final linear momentum is this m minus del m into v dash plus del m into v equals to mv, and after rearranging we will get v dash equals to v. So what it is saying is that this, and it is very intuitive and you can say directly also, that when this mass is ejected with same velocity v in the same direction of motion, so this remaining mass will also have same velocity v. So in that case there is no change in momentum of this del m, neither there is change in momentum of this remaining mass. So neither this is experiencing any force nor this remaining mass is experiencing any force. So there is no injection of, you can say, energy or force. There is no kind of force which can increase or decrease its amplitude. So whatever is shown in the solution, that amplitude is in fact decreasing, or in some cases it is shown that amplitude is constant, that is not possible. So this is what my solution says. Thank you.